How is everybody? Right. I am also good. I'm also Zach Palmer. This is joint work with Scott Smith, and this is DDPA, which is a higher-order demand-driven program analysis that I'm going to be talking about. And just to make sure we're all on the same page, I've put just a handful of program analyses up here. In this dimension, I've separated things by first order and higher order, which is going to be simply whether or not I have a notion of control flow when the analysis starts, or if I build it as the analysis proceeds, right? Up here, I've got a distinction between push-forward analyses and demand-driven analyses, just whether I accumulate values for variables as the analysis moves forward, or if I wait until I need the value of a variable before I try to compute its values, right? And this box on the bottom right here is conspicuously empty, and that's what I intend to talk about today. Our analysis fits into that space. I do want to make sure I mention that there was a work about 15 years ago that appeared in Popple. Riehoff and Fandrick had this system called Polyflow CFL. It's a constraint-based type system. They have this notion of instantiation constraints, and it winds up sort of, it's near to this space, demand-driven and higher order, but all of the analyses in these boxes have at least some form of flow sensitivity. So that's one dimension of difference here. DDPA is a flow-sensitive analysis. Also, we have a degree of precision here that you don't wind up seeing in that work. Okay? So I'm going to be talking about this demand-driven, higher-order, flow-sensitive program analysis. That's the point of the talk. Okay? So I'm going to start by example. Right? I'm going to go through this little simple OCaml-like program. Right? Just calling the identity function twice. And the first step I'm going to go through, just to make the presentation a little more straightforward, and because it makes the algebra easier in the analysis, is to anormalize that code. Okay? So this is just an anormalized version of the code above. From that anormalized version, I can get this sort of partial control flow graph, because, you know, as common in higher order analyses, I don't know exactly where all of these call sites are going to go. I have to wait until runtime values show up. Okay? Once I've got this approximation of control flow, like this partial control flow graph, then I can actually do my analysis. And again, if this were a push-forward sort of analysis, I'd start from the start of the program, and I'd just start moving forward, aggregating values into like an abstract heap or something. I'm going to do this in a demand-driven way, which means I'm going to look for the first call site that I don't know where it goes, right? The first call site for which I don't know what control flow is going to be. And from that point, I know that control flow is determined by this function I'm calling, right here, ID. Since I want to figure out what control flow occurs at this call site, I need to know the value of that variable ID so I can find the function I'm calling. And so I'll just start from this point, and I'll look backwards in the program. I'm looking for a definition of ID, starting from the point of the use site. All right, obviously N1 isn't it, so I'm just going to keep going. And eventually I find this definition of ID, and I figure out exactly which function it is I'm trying to call, right? There's the body of the function I'm calling. So in order to represent the fact that call site S1 passes through that the body of that function, I'm going to start at the point immediately beforehand, and I'm going to add this wiring node. Okay? X here is the parameter of the function. I'm just assigning the value of the argument at the call site. And then I'm going to add this exit wiring node here that passes the result of calling the function into the call site itself, right? S1, this call site variable, is being set equal to the return value of the function. And so now I've wired in that function call. Okay? At this point, I've finished analyzing call site S1, so I'm just going to repeat the same process for S2. I look backwards. I find the definition of this function ID. Oh, look, it's the same body. Now note, I'm not copying the body in the graph at this point. I'm just wiring in to that point in my program, and then wiring back out again, the same as I did before. Okay? And I'm showing this example to give you an idea as to where we're coming from with this analysis. At this point, this is a sort of control flow graph for my program. Okay? Just to summarize, I did incrementally build a CFG, right? That's higher order program analysis kind of needs to do that because control flow is affected by data flow. The function bodies I wired in on an as-needed basis, and the entire analysis sort of focuses around this question. Given a point in the program, what values might a certain variable have, right? It's not an uncommon way to phrase it, but this process was quite specifically on demand. I waited until I needed the variable, and then I just walked backwards through the program to find the definition. Okay? So this seems really simplistic, and you've got to be asking, like, how could this wind up being accurate? Here are a few challenges. Can people read that text from back there? I'm not entirely sure how clear the slides are. We've got many challenges we could be talking about right now. Today I'm only going to have opportunity to talk really in depth about the first two. I'm also going to briefly mention recursion. It doesn't take terribly long to outline what we're doing there. I should mention flow sensitivity comes for free. That's one of the things about this analysis. That question I'm asking, from a given program point, what could the possible values of this variable be? This question is just fundamentally flow sensitive, right? The way that I'm sort of starting from a point and moving backwards and trying to figure out what values occur in this particular variable, okay? So let me talk about that first problem, right? Aligning call stacks. This is a common program analysis, common problem program analyses have to address. And I'll just illustrate the problem by asking a certain question. What value could the variable s2 have? This end variable. What value could that have by the time my program is finished running? So I'll start at the end of my program and I'll walk backwards looking for s2. Here I find out that s2 is defined in terms of this variable ret. So really, if I wanted to know the answer to that question, I could walk back looking for ret now, right? That would be my answer. And I can keep doing this like by definition, ret is equal to x, and so I'll walk back a couple of times, and I'll eventually find this definition n2, and that's the value of my s2 call site, right? I passed 2 into the identity function, and so I should be happy to get that value, right? That's the answer I was looking for. But of course, because I didn't do any kind of copying in the graph, if I just naively do this, I could also have taken that path, right? In looking for x from ret, I could have wound up taking that other entrance wiring node, and I'll wind up getting an answer I didn't want to see. And the reason for that is, of course, because here, this wiring node, this entrance, was related to that S1 call site. This appeared in the graph because of that S2 call site, and so I've got this sort of alignment problem. We're going to take a solution that's similar to solutions that we've seen in other program analyses before, and just sort of maintain this call stack during lookup, right? So what I'm going to do is add to this graph a collection of annotations, which you probably can't see very clearly, but I'm going to mark each of the wiring nodes with which call site it came from, and then keep track of a sort of abstract call stack, right? So again, starting from the end of the program, going back trying to find the point of definition, I see that I'm looking for S2. Here I'm looking for ret in the context of a call from site S2, okay? And so this path is still valid because here I see I'm moving through the entrance node for S2, and so I wind up getting that n2 value, and I'm good. But this faulty path I had before is now prohibited because my sort of abstract call stack can tell me, oh, well, like, I can't pop S1 off at the top of that. This wiring node doesn't line up, right? This function entrance doesn't line up the way that you got into the function from the tail, right? A lot of this is very topsy-turvy because I pushed S2 onto my stack because I entered the end of a function while looking backwards through my graph, okay? And then when trying to leave the top of the function, I expect that to be lined up. So at this point, I wind up just getting the value 2, and so that alignment kind of helps me address that initial imprecision. To summarize, like to look at this alignment problem, there are all sorts of program analyses that do some form of call stack alignment like this, right? CFA2, PDCFA, they use a pushdown system in order to line up these sorts of things. Pushdown system stack. A PDA stack is able to match parentheses in a sense, right? So you can match calls and returns and use the PDS to validate the path that you take. These analyses don't align non-locals that way. They actually wind up doing that sort of context copying, that sort of graph copying in order to address that. This polyflow system I mentioned before, the one that is sort of near our space, it actually also uses a context-free language to make sure that calls and returns are aligned, right? So these two are similar in that capacity. Call return alignment is accomplished through a CFL-like structure. Although again, this analysis is not flow sensitive, and there's a certain degree of precision we wind up getting out of the thing I'm showing you today that I guess I don't really have a lot of time to talk about. So we're going to actually use a similar approach, similar in that we're going to wind up using a pushdown system for our analysis. It turns this question, from this program point, what values of a certain variable could get here, starts to turn that question into a pushdown system reachability question, right? What value nodes can I reach from this point in my automaton? But we can't use the PDS stack as the program call stack. We can't, abstract the call stack into the PDS because we're going to need that stack for something else, okay? This is the second problem that I was highlighting, this non-local variable handling. If I'm going to use this pushdown system in order to do my variable lookup for this sort of backwards flowing analysis, then it turns out that non-local variables need special handling, right? Like they're sort of fragile. I need to be careful about what I do here. Take a look at this example program. This is the K combinator, right? Given any two arguments, the first argument is the thing that it's going to return. So here I have this function f, which given anything will return 1. G given anything will return 2. And so I'd expect on line 4 here that s would be the value 1, right? Whatever f returns. Just like before, I'm going to anormalize that, okay? And I'm going to wind up building this sort of initial call graph, the control flow graph. And in this control flow graph, I'm going to walk through the same process. I see a call site that doesn't have any wiring, right? That might have an additional function showing up at it that I haven't wired in yet. So from f, I see that k is in fact the function that could be wired. So the body, which is just this k0 node, winds up getting wired in at that point, right? Again, g is a call to k. The value of g is established by calling the k function. So I do a similar wire in there. And then down here, f is actually sort of like the body of this inner function here, this r variable. So s is going to wind up calling f, and so I wire in that body there. Everyone with me there? So once I've constructed this, I want to look up s from the end of my program. I should be able to do that, right? It's a fairly simple question to ask an analysis like this. And so I'm going to wind up doing what I did before, complete with this sort of abstract call stack. I can keep walking backward, and I can see, like, oh, here I'm looking up, for instance, r in context s. Okay? I get to this point, and I'm looking up v, and then that happens, which makes me very sad, right? Because if I just follow the graph as I've been doing before, it makes it look like v's not bound, right? It makes it look like v's a free variable, and we know that's not true. If you just look at this program, r is defined in terms of v, which is the parameter captured in the closure of this k0 function. So the reason this happened is because this is actually giving us it's sort of violating our assumptions about this lexical scoping we assume the language has, right? The variable v was captured at the point that this k0 function was defined, right? Captured in the closure of the function. So the real problem here is that when I left this function looking for something other than its parameter, looking for something captured in its closure, I tried to look for it from this point where it was called, rather than from the point where the function was, like the closure was captured in the first place. So if I want to figure out what the value of v is from this point, what I need to do is actually start looking up the function in its closure, right? I need to find the function itself, and then once I've found that function, then I can resume looking up v and actually find my answer. Okay? So the trick here is that I need to find the closure of the function whenever a non-local variable is accessed. Whenever I need the value of a variable that's non-local to a function, I need to hunt down the function's closure and look inside of that closure. And since I'm doing all of this demand-driven, I need to hunt down the actual definition of that function, and this can happen at multiple levels. So in the general case, I might have this sort of stack of lookups I need to perform, right? Once you're done looking up what you're looking up now, then you need to look up this next thing, and after that you need to look up this next thing, and so on. And so I need that stack of continuations, in addition to that abstract call stack I was talking about before. And now we have a problem, right? Because I've just built a Turing machine, and that makes me sad. So I'm going to address that by finitizing the call stack into the PDS nodes. What I'm going to do is keep the top k frames of the call stack. I'm going to call that KDDPA. Okay? What that does is leaves the PDS stack open for this continuation stack. And I'm going to use that as the stack of the PDS when I'm asking this reachability question. So, this still translates into a PDS reachability problem. It's just the stack of the PDS is this lookup stack rather than the call stack from before. I said I was going to mention recursion briefly, so let me briefly mention recursion. If you take a program with recursive function calls in this analysis and just look at the PDS that comes out of that, you wind up getting a PDS with a cycle in it. Cycles in a PDS are no big deal when you're asking a question about reachability, right? They're sort of naturally eliminated by reachability. This is a point of precision loss in the analysis, because I can't tell how many times you've gone around that cycle, but I can tell that, at the very least, whether something could be reachable or not. Right? This is a sort of conservative approximation of how recursion executes. It's actually very similar in expressiveness to other analyses approach to collapsing recursive cycles. Okay? So that just kind of falls out of using a PDS in this way. We have demonstrated that KDDPA, for a fixed k, has a polynomial time bound. Right? Any lookup operation is polynomially bounded in the size of the program. This relies heavily upon the fact that the PDS that represents the control flow graph is monotonically growing throughout the analysis, which means that I can reuse this same structure over and over again as I learn more values for each of my variables. Okay? The thing is, this entire analysis then becomes this push-down reachability problem, and it winds up actually being pretty fast in practice. So to give you an idea as to what the whole analysis looks like, here's another simple little, I call the identity function. Here's the control flow graph I wind up getting after I close over it. And then this picture on the bottom is what the fully closed push-down reachability graph looks like, right? So here's a push-down system. It's got a series of pushes and pops. And when I close over this question, what could the values of z be, I wind up getting this chain of no-ops back to the variable, which is actually the value that z could take on. Okay? Just to compare with sort of state-of-the-art forward analyses, it's definitely true that forward analyses are more intuitive. You can essentially read a forward analysis off of the operational semantics of the language as long as you know how to abstract those operational semantics carefully. Right? You can take the operational semantics of the language, move them into an abstract space, and there you go. There's a program analysis, modulo all of the things you have to do in order to make that program analysis nice and precise. So in a certain sort of sense, this backwards approach is less intuitive. But it also could be potentially more efficient because due to the way that we're actually doing this lookup, we're only reaching for variables that we see are used. We never actually move a state forward if it, with information that we might not use in the future. We wait until something is necessary until we actually do the work to look it up. Asterisk all of the precision of the analysis, right? So I should point out that the k in KDDPA, you can't think of that as being identical to the k in something like KCFA. In particular, we need a larger k in order to handle this, to give the same degree of precision, specifically because that k is used both for non-local variable lookup and for context precision. Okay? And hopefully this is fairly intuitive just because KCFA is exponential time for any positive k, and I just claimed that we have a polynomial analysis, so if I said that these k's were the same, then I'd obviously have contradicted myself, right? In practice, it seems that these things are similar in expressiveness. Okay? We do have an implementation, though I should point out the paper artifact is a proof of concept, and it is slow. It is very slow. We have since constructed a more efficient implementation that actually includes several language features. We've got records. We provide a degree of path sensitivity, and we provide a stateful analysis as well, we can handle ref cells. And those are both handled by embedding the question, for instance, the alias analysis into the PDS. There's not an external algebra doing that work. It's all still a reachability question. Our implementation actually is lazily constructing this PDS as, according to an abstract definition, as we're doing our lookups, because it turns out that especially with path sensitivity, this PDS is massive, but for any particular question, or even all of the questions you might want to ask to make sure that you never apply a non-function to a particular program, you only need a very small amount of that abstract definition in order to answer all of those questions. Okay? So far, it looks to be reasonably efficient, although I should point out that's not something that came from our paper. That's work we're doing right now. So in the future, I'm hoping for, we're working on a sort of variable alignment refinement so that when you look up variables, they actually have something to do with each other, right? If I look up x, I only get values of x that actually match the values of y that I also looked up. We actually have, we're working on a better call stack model, because right now I keep the last k things kind of blows up a bit when you ask recursive questions. And we're hoping to eventually take this analysis and apply it to quote-unquote real languages. That is to say, languages that somebody has written code in who aren't us, right? So JavaScript or Python or something like that. Summarization. As far as we are aware, this is the first flow-sensitive, demand-driven, higher-order program analysis. The program analysis is based on this sort of incremental model checking problem, this PDS reachability problem, which we're thinking is quite promising for efficiency. All of our initial tests are looking nice. It appears to be comparable in expressiveness with state-of-the-art forward analyses. And if you're interested, you can find the code on GitHub. Does anyone have any questions?
I liked your presentation by way of examples, but the simple examples you went through on the slide don't really help me understand how this works in a typical program where the method you're requesting is on a target that comes out of an instance variable that was filled in some completely different part of the program, minutes before. And the flow problem is not just walking back a few steps in the current method. It's far, far more complicated. Could you talk about that just a little bit?
Sure. Obviously, such a graph, such a PDA wouldn't fit very nicely on a slide, which is why I deleted those. But you make a good point. On a larger graph, you want some assertion that the path is not going to get so long that somehow you lose all of the precision that you want. As it turns out, the reachability in the PDS winds up sort of collapsing cycles or chains, right? So often in that sort of situation, I want to look up the object that the method is on. In order to look up that object, I need to, for instance, look up the value of some other local variable. And the thing is, each of these lookups wind up in the PDS collapsing to just a single no-op arc to the appropriate node, as if they were their own question. Which, as a result, means that the larger K I was talking about, so far as we can tell, in order to prevent yourself from losing precision over something like KCFA, the additional thing that we add to K, and this is a sort of conjecture, it's not a proof, is the lexical depth of the program that you're in, right? So the worst case scenario is that it's just a series of nested functions, and the entire, the size of the program is n nested functions, and so your lexical depth is equal to the size of the program, at which point that fixed constant becomes the size of your program and the analysis is exponential again. But in practice, as long as the lexical depth isn't enormous, then you should be fine. Does that make sense? Yes?
Yeah, thank you for your talk. I really enjoyed it. I'm back here.
Yes. Hello.
I'd like you to say something more about your K parameter. I mean, you identified pretty clearly that it's different than the KCFA K parameter, but you also say that it captures a kind of call site sensitivity. So how are you capturing call site sensitivity if you're not the same as the other K parameter?
So it does that in that, if I have 4 DDPA, then ignoring non-locals, I can handle 4 levels of call. But if I have non-local variables, every time I need to push one of those, look up the closure of this function onto the stack, that also occupies a slot that I would otherwise use for a calling context. And so what I was just alluding to is that if I have K plus some lexical nesting depth of the program, I should have similar, if not identical, expressiveness. Does that answer your question? Yeah. But if you want further clarification, please find me later. Any other questions? Do I have time for other questions? Well, if you think of any, please hunt me down. I like talking. Can you tell?
All right, let's thanks the speaker, Zachary.